Our question in this video is, how is mass similar and different than moment of inertia? Well, when we talk about mass, mass is a measurement of how much inertia an object has. And inertia, if you don't remember, is how difficult it is to make an object start moving or to bring an object to a stop. Inertia is the tendency to just keep moving the way it always was. Moment of inertia is really the same idea, only applied to a spinning object. So the moment of inertia is an object's resistance to changing its rotational motion. If an object is spinning, it wants to keep spinning. And the number of the moment of inertia, so it's going to be a number, the number tells us how difficult it is to stop the object from spinning or to get it started spinning in the first place. For example, if we have two tires, let's say we have a bicycle tire, and we try and spin that bicycle tire. Well, it's very easy to spin that bicycle tire. But if we look at a tire on a tractor, okay, a tractor tire is much bigger. It's usually more contoured there as well. A tractor tire is much more difficult to spin. That's because they have different moments of inertia. The tractor tire has a larger moment of inertia than the bicycle tire. The larger the moment of inertia, the more difficult it is to spin it, or the more difficult it is to get it to stop spinning once it is moving. So therefore, the larger the moment of inertia, the more difficult it is to rotate the object or stop it from rotating. Now, just like mass, moment of inertia is a scalar. It's just a number with no direction. The symbol is the letter I. I standing for the inertia part, versus the symbol for mass, which is N. The units for moment of inertia are a kilogram times meter squared. And the equation really depended upon the shape of the object. Now, there's a few things that affect the moment of inertia. One thing that affects the moment of inertia, like when we looked at the bicycle tire, is the mass itself. The more mass it has, the more difficult it is to start spinning or to stop it if it's already spinning in the first place. The second thing that affects it is the radius or length. The wider it is, the more difficult it is to start it spinning or to stop it if it's been spinning in the first place. So if we have two bicycle tires, each of the same mass, the one that has a wider radius is going to be more difficult to spin than the one with the smaller radius. So if they have the same mass, this one being a wider radius will still have a larger moment of inertia. The last thing that affects the moment of inertia is the mass distribution. Or the shape of the object. And this is what determines then this number that's going to go in front of our equation. For example, if we have a solid sphere, like the Earth, or a billiard ball, or something like that, well, then the moment of inertia is going to be 2/5 the mass times the radius squared. So that coefficient in front is 2/5. But if it's a thin shell of a sphere, kind of like a basketball or a tennis ball that's hollow in the middle, then the moment of inertia is 2/3 the mass times the radius squared. notice that the coefficient is a bigger number. If more of the mass is located on the outside, it is going to have a larger moment of inertia. If I have something that is a solid disk that is spun around the symmetry axis at the center, then the moment of inertia is going to be 1/2 the mass times the radius squared. That coefficient is 1/2. But if it's more of like a hoop, this would be like a solid disk here, versus a hoop, kind of like that bicycle tire. If it's a hoop, the moment of inertia is simply mr squared. The coefficient is essentially 1, if you wanted to write that in there. So just by the shape alone or where the mass is located, that will affect the moment of inertia. We also have, if we have a rod, and how it is spun. So if we have a rod that is spun around the middle, so if you hold, let's say, a meter stick in the middle and spin it, rotate it with your hand. Well, in this case, the moment of inertia is 1/12 the mass times the length squared. But if you try and spin it instead at one end like a baseball bat, if you spin it from this point and spin it around like a baseball bat, even though it's the same meter stick, now the moment of inertia is 1/3 the mass times the length squared. It's much more difficult to spin something from one end than to spin it from the center. That's because more of the mass is located further away. The further away the mass is located, the more difficult it is to rotate the object. So to recap, the moment of inertia is an object's resistance to changing its rotational motion versus mass, which measures how difficult it is to change its linear motion. The larger the moment of inertia, the more difficult it is to rotate it or to stop it from rotating, similar to inertia itself, which is how difficult it is to get it to start moving or stop moving in a straight line. Both mass and moment of inertia are scalars. The symbols and units, of course, are different. And we see that moment of inertia doesn't depend just on the mass. It also depends on the size and also where the mass is located for the shape.